So, last week, a humanoid robot actually learned how to sort heavy machinery parts on a factory line. And it didn't learn by, being manually programmed line by some engineer.
Right, yeah.
It learned by watching a human operator in virtual reality and then running like 1,000 video game simulations overnight and updating its physical brain by morning.
Which is just wild to think about.
It really is. The hardware involved in this is incredible, but well, okay, let's unpack this. Because if you work in enterprise data or AI or, tech strategy, that hardware is actually a massive distraction.
Oh, totally. 100%.
That robot's brain is basically about to break your entire data pipeline.
Yeah, the shiny metal is always what grabs the headlines, right?
Right.
But the real story is entirely invisible to the casual observer. And the true mission of our deep dive today, which is based on a really eye-opening June 2026 article from datapro.news by Samuel Williams, is to explore how physical AI is totally blowing up and rebuilding enterprise data architecture. The core premise here is that intelligence has officially, moved off the server racks and stepped out into the physical world.
And the stakes for you listening right now could not be higher because the robots are already in the building.
They really are.
And the terrifying part that Williams points out in his article is that most enterprise data stacks are just completely unprepared for them. I mean, people are still treating robotics as someone else's problem.
Yeah, it's just a mechanical engineering issue.
Exactly. But to understand why your data infrastructure is about to completely shatter, we have to look at how the actual brain of the AI has changed over really just the last 18 months.
Yeah, we really need to contrast this with the era everyone is comfortable with right now. Let's look at early 2025.
Okay.
Enterprise data teams were obsessing over large language models, setting up RAG frameworks, fine-tuning batch ETL pipelines, deploying vector databases, all of that.
The classic text stuff.
Right. But think about the fundamental nature of an LLM. It is entirely passive. It just sits in a server waiting for a text prompt.
Yeah, you type a query, it generates an answer, and then it goes back to sleep.
Exactly. But with the shift toward large behavior models and now vision language action models, or VLAs, that paradigm is just dead.
It's completely gone.
We have moved from, query the model to the model is always running, always sensing, always acting.
It's like the difference between a search engine and a self-driving car. I mean, the search engine waits for you to type a question. It does nothing until you act.
Right. It's totally reactive.
But the self-driving car is constantly reading the road, checking its blind spots, feeling the traction on the tires, and steering, all simultaneously. It doesn't wait for a prompt from you to avoid hitting a pedestrian.
Right. And the implication of that constant active state is staggering for systems design. And the VLA models take this to a level even a self-driving car architecture struggles with.
Oh, really? How so?
Well, what a vision language action model does is collapse what used to be 3 highly siloed layers of robotics into one single layer.
Okay, break that down for me.
Historically, you had a perception system to, see an object, then a planning system to calculate how to approach it, and finally a control system to actually fire the motors in the robotic arm.
So 3 separate models.
Yes, 3 separate models passing data back and forth, which, as you can imagine, introduces massive latency.
I'm picturing like an incredibly bureaucratic office. The eyeball department fills out a form and sends it to the planning department, who then drafts a memo and mails it to the arm department.
That's actually a perfect way to describe it.
And by the time the arm gets the message, the object you were trying to pick up has already fallen off the conveyor belt.
Exactly. That is exactly the latency issue that plagued early robotics. But a VLA model eliminates the bureaucracy entirely. It is a single, unified neural network.
So it's doing it all at once.
Yeah. It takes in visual input from its cameras and natural language instructions from a human operator, and it outputs low-level motor control commands directly to the joints.
That's wild. And this is what was running that Atlas robot, right?
Yeah. Yep. The Atlas robot that made that massive splash at CES in early 2026, the one doing backflips with a 50-kilogram payload and those crazy 360-degree joint rotations.
It was so cool to watch.
It operates on this exact VLA architecture, which they developed in partnership with Google DeepMind and the Toyota Research Institute.
And this isn't just a niche experiment anymore. The article mentions that at the ICLR conference in 2026, there was an 18-fold increase in VLA-related submissions compared to the year before.
Yeah, an 18-fold jump in 1 year.
That represents a massive brain drain from traditional text-based AI research straight into physical AI.
Oh, absolutely.
but going back to that always-on nature, because if I try running a continuous data feed like that on a standard enterprise pipeline, things start to bottleneck almost immediately. How are companies actually ingesting all this data without their servers just catching fire?
Well, they're having to completely rethink the shape of the pipeline. If we connect this to the bigger picture, a traditional data pipeline is essentially a straight line.
Right.
You ingest data, you clean it, you train a model, you deploy it, maybe you update it once a quarter. But
Yeah.
physical AI introduces what Williams call the physical AI flywheel.
The flywheel.
Yeah, it is a continuous multimodal loop operating at a scale that is honestly hard to comprehend. A single humanoid robot on a production line generates terabytes of data per hour.
Terabytes from one machine in an hour. I mean, most companies don't process that kind of volume across their entire software suite in a week.
I know, and the sheer volume is only the first hurdle. The real complexity lies in the variety and the speed of that data.
What do you mean by variety here?
You are dealing with simultaneous multi-rate streams. So on one channel, you have joint-level telemetry, the actual physical position of the robot's motors pinging at 1,000 hertz.
So 1,000 times a second.
Exactly.
Yeah.
And simultaneously, you have RGBD cameras capturing visual frames and depth data at 30 hertz, alongside, tactile sensors on the fingertips and 3D point clouds mapping the room.
Okay, wait, let me slow you down because the math on that time alignment sounds terrifying for a data engineer.
Oh, it is.
If the robot's joints are reporting their position 1,000 times a second, but the camera is only taking a picture 30 times a second, I mean, for every one visual frame, the robot's knee or wrist has updated its position 33 times.
Yes. And that mismatch is exactly where enterprise data architectures break down. Time alignment between a haptic touch signal and a visual camera frame is no longer just some nice-to-have pre-processing step where you round to the nearest timestamp.
Right.
It is load-bearing infrastructure now.
Here's where it gets really interesting, because the consequence of getting that timestamp wrong isn't just, a glitchy dashboard.
Not at all.
If a data engineer uses traditional streaming tools and misaligns those data streams by just 50 milliseconds, the model actually thinks the robot was holding an object before the camera saw the hand close around it.
Yeah, you fundamentally corrupted the causality of the training data.
In a text-based LLM, bad data means the chatbot gives you a historically inaccurate answer about the Roman Empire. But in physical AI, bad data means you ship a model update that causes a 90-kilogram robot to just drop a heavy metal part on a human colleague.
The feedback loop is physical, and the margin for error is effectively zero.
Precisely.
Which brings us to a massive bottleneck in the flywheel. Let's say you figure out the ingestion. You're successfully capturing terabytes of perfectly time-aligned data from the factory floor.
Okay.
The article highlights Hyundai's Georgia megaplant, where edge cases like a robot failing to grip a weirdly shaped, oily car part are flagged and sent up to the Robot Metaplant Application Center, or RMAC.
Right, the RMAC facility.
The idea is that the robot struggles on Tuesday, the data gets processed, and by Friday, the entire fleet has learned how to grip that specific part. But with terabytes of data flooding into RMAC every hour, how on earth do you filter the gold from the garbage?
Well, this requires discarding basically everything data teams currently believe about data quality.
Really? Everything?
Pretty much. In enterprise analytics, data quality is defined by completeness, freshness, and schema compliance. If all the fields in the database are filled out in the right format, it's considered high-quality data.
Right, that makes sense for text or numbers.
But physical AI introduces a completely new metric. They call it learnability.
Because a lot of this initial training data doesn't come from the robot itself, right? It comes from human teleoperators.
Yes, exactly. People wearing VR headsets and haptic gloves, physically guiding the robot through a task on the factory floor so the AI can watch and map the visual input to the motor output.
But humans are messy.
The problem with human teleoperation is that humans are incredibly noisy data generators. The question isn't whether the data record from that VR session is complete or valid. The system recorded it perfectly.
So what's the actual issue?
The question is whether the human's demonstration actually contained a useful signal for the neural network. Did the specific action sequence the human took tell the model something informative about manipulating that environment? Or was it just random noise?
Okay, I think I have an analogy for this.
Let's hear it.
It's like if you're in the passenger seat trying to teach someone how to drive. High learnability is when a dog runs into the street and you carefully and deliberately turn the steering wheel to avoid it, showing the student exactly how to react to that obstacle.
Yes, perfect.
And low learnability is you just waving your hands around to the music on the radio while you happen to be driving. I mean, the recording device in the car captures both movements perfectly.
The data is completely valid.
Right. But if the AI tries to learn how to drive by watching you wave your hands to the music, it's going to crash immediately. It doesn't know what on earth to learn from that action.
Exactly. And when you map that exact concept to mathematical data processing, you arrive at something researchers call mutual information estimation.
Mutual information estimation.
Yeah, it is a mathematical way to calculate the statistical dependence between the states, what the robot's cameras and sensors were experiencing, and the actions, which are the physical movements the human teleoperator was making.
So high mutual information means the humorous movement was a direct, calculated response to the environment, like avoiding the dog in the street.
Precisely.
And low mutual information is the hand waving. There's no coherent relationship between the environment and the action.
You've got it. And you can actually write algorithms to programmatically score this mutual information across terabytes of data.
Wow, at that scale.
Yeah, this is what the RMAC facility at Hyundai is pioneering right now. They have automated scoring pipelines that ingest human demonstrations, calculate the mutual information estimation, partition the dataset by these quality scores, and aggressively discard the noise.
That's incredible.
The conceptual muscle of building a data quality pipeline is familiar to enterprise teams, sure, but the domain expertise required to calculate physical learnability is entirely new.
But even if your data engineering team builds the perfect mutual information filter, there's a harsh reality here, right? Relying on real-world human demonstrations is just hopelessly slow. I mean, the datapro.news piece highlights Google's RT1 project. It took them 17 months to gather 130,000 real-world demonstrations.
17 months is an eternity in AI.
Yeah, 17 months of humans walking around in VR suits just to get a baseline data set.
Well, compare that timeline to NVIDIA's GR0T Dreams blueprint, which was released shortly after. The NVIDIA system can produce equivalent volumes of highly complex training data in a matter of hours.
Wait, hours? Without a single human putting on a VR headset?
Completely synthetic.
Does that even work?
The data engineer feeds the system a single static image of a factory workspace and a language prompt, like, move the yellow bin to the top shelf.
Just a text prompt and an image.
Yeah. And the system leverages generative AI to create diverse video sequences showing various ways that action could play out in the future. But obviously, a video isn't motor control data.
Right, a robot can't just watch a video and know how hard to squeeze its hand.
Exactly. So they pass those generated videos through an inverse dynamics model.
Okay, wait, inverse dynamics model, I've seen that term thrown around a lot in robotics papers recently. How does a video actually turn into physical instructions?
Think of it as working backward from the answer. Instead of the traditional method where you tell the robot to fire a specific motor and then wait to see what happens to the environment, you show the model the end result.
The synthetic video of the completed task?
Right. The inverse dynamics model looks at that video and reverse engineers the exact physics, the joint torques, and the motor trajectories that would be required to physically achieve what is happening on screen.
So it looks at a video of an arm lifting a box and calculates, mathematically, how much strain would be on the shoulder joint, how tight the grip needs to be, and basically translates pixels into physics.
That's exactly it. It translates pixels into executable 3D action trajectories, and then it filters those trajectories for physical plausibility.
Meaning making sure it doesn't break itself.
Yes, ensuring the robot wouldn't accidentally break its own arm trying to replicate some weird AI video artifact, and then it pushes that synthetic data straight into the training pipeline.
So what does this all mean for the people listening? It means you, the enterprise data engineer, are now essentially managing a massive, hyper-realistic video game simulation.
That is exactly what it is.
Platforms like Isaac Sim, Cosmos, Omniverse, these aren't just cool research tools anymore. They are mandatory production infrastructure.
Absolutely mandatory.
You are generating synthetic edge cases, running the inverse dynamics models, and teaching the robot inside the matrix before its physical metal feet ever touch the factory floor.
And the data supports this shift unequivocally. VLA policies trained on a mix of real and synthetic data consistently and significantly outperform models trained on real data alone.
Really, synthetic makes it better than just real data.
Yes, because if you only train on real-world data, the robot just memorizes the exact lighting conditions and the specific layout of the factory where the data was gathered.
Oh, I see. It gets overfit to that one room.
Right. Synthetic data allows you to simulate thousands of environmental variations, harsh shadows, narrow corridors, novel objects dropped on the floor.
So the model learns generalized physics rather than just memorizing a specific room.
Exactly.
All right, so we've solved the brain. We have the unified VLA model collapsing perception and action. We've built the continuous data flywheel. We're filtering for mutual information. And we're supplementing the slow human data with high-speed synthetic video game simulations.
We're doing a lot.
We really are. But eventually, this massive digital brain has to get downloaded into a piece of physical hardware. Where does the actual computing happen when a robot is walking around a crowded warehouse?
That is the million-dollar question.
Because it can't possibly stream every single decision to an AWS cloud server and wait for a response before deciding not to step on a forklift.
No, the latency of a cloud round trip would be catastrophic in a dynamic physical environment.
It would just crash into everything.
Yeah, and this introduces an absolute MLOps nightmare, which is the edge-cloud architecture split. The economic and physical safety realities are forcing companies to solve this on-device compute problem immediately.
So how are they doing it?
The article points to NVIDIA's Jetson Thor module as the current gold standard here. It provides enough raw on-device compute power to run both the high-level VLA reasoning model and the low-level motor control loop simultaneously directly inside the robot.
I'm struggling to picture how that works safely, though.
What do you mean?
Well, let's say the robot is looking at a massive chaotic pile of overlapping metal parts on a conveyor belt. The reasoning brain is suddenly maxing out its computing power trying to parse that visual mess. What stops the computer from freezing up, causing the robot's legs to just shut off and dropping a heavy machine in the middle of the floor?
Ah, okay. That exact safety concern is addressed through hardware isolation, specifically a technology called multi-instance GPU partitioning, or MIG.
Okay, MIG. So the computer chip itself is physically walled off.
Yes. You partition the GPU hardware into isolated instances. You dedicate a specific, unpreemptible slice of the GPU solely to the low-level motor control and balancing loop.
So the legs get their own dedicated brain space.
Exactly. And the high-level VLA reasoning model gets its own separate slice. This hardware isolation guarantees that no matter how hard the reasoning brain is thinking about that pile of overlapping parts, it physically cannot steal computing power from the balancing brain.
Wow. So the robot might stop moving its arms while it thinks, but its legs will never freeze up and collapse.
Precisely. Safety-critical systems always stay online.
That is fascinating. But think about the MLOps pipeline required to support a fleet of these edge compute modules. You have a warehouse full of robots generating terabytes of data at the edge. You can't pipe terabytes of raw video and telemetry over a basic factory Wi-Fi network.
No, you definitely can't, which is why the MLOps pipeline has to be bidirectional and highly selective.
Selective, meaning it doesn't send everything back.
Right, the on-device computer has to act as a triage center. It recognizes when it encounters an anomaly like an edge case it hasn't seen before, packages that specific snippet of telemetry and video, and selectively syncs it up to the central cloud infrastructure like Hyundai's RMAC.
And then simultaneously, the central cloud is pushing newly trained model updates back down to the fleet.
Yes, with strict version control, rollback capabilities, and continuous integration testing. I mean, most enterprise data teams have never built a bidirectional deployment pipeline like this in a safety-critical context at fleet scale.
And they do not have the luxury of waiting a few years to figure it out because the economics of this are just brutal.
Oh, the economics are undeniable.
Samuel Williams drops an absolute financial hammer at the end of the article. An advanced humanoid robot, fully operational, amortized over its lifespan, including energy and maintenance, costs an estimated $5.71 per hour to run.
It's staggering, especially when you compare that to the fully burdened cost of a Humi warehouse worker, which sits around $28 per hour in the U.S.
The ROI case for humanoid deployment isn't some theoretical debate for a 2030 boardroom anymore. At $5.71 an hour, the decision has already been made.
Yeah, the robots are in the building.
It's the data infrastructure that is lagging behind.
So the mandate for anyone listening to this deep dive is to stop treating robotics as a hardware curiosity and start upgrading your data stack for physical AI immediately.
Okay, let's synthesize the urgent actions you need to take right now if you are anywhere near an enterprise architecture. Number one, you have to stress test your streaming architecture.
Absolutely.
Think about your ingestion layer today. If it was built for asynchronous structured text events, How is it going to handle simultaneous 1000 hertz telemetry and 30 hertz video that requires millisecond exact time alignment? You need to run that load test on Monday morning.
And the second action is expanding your peen's vocabulary. You need to learn mutual information estimation. Understand what learnability means in a mathematical context.
Even if they don't have robots right now.
Yes, because even if you aren't deploying walking robots today, any industry where AI trains on human behavior, whether that's complex customer service routing or dynamic supply chain decisions, will eventually need to calculate whether human actions are actually informative or just noise.
That's a great point. Number 3, you need to build a synthetic data pipeline now. It doesn't have to be a massive rollout.
Start small.
Yeah, pick one small use case. Spin up an environment in NVIDIA Omniverse or Isaac Sim, run an inverse dynamics model to generate a small, physically plausible data set, and inject it into a real training run. You have to build the organizational muscle to manage and version control simulated video game data.
Fourth, redesign your MLOps for bidirectionality. Look at your current deployment stack. If it only moves models in one direction, from a central cloud training server down to a production environment, it will completely fail when physical AI demands that you push model updates down while simultaneously pulling massive selective edge case telemetry back up over constrained factory networks.
And finally, number 5. You must start building a data provenance story for physical AI immediately. These robots are rapidly moving out of controlled labs and into highly regulated environments like automotive assembly, electronics manufacturing, and eventually healthcare.
Which means auditors.
Oh, yeah. The second a physical AI makes a mistake that causes property damage or injury, auditors are going to knock on your door. They won't just want the logs. They will want to know exactly what specific synthetic and human data trained the reasoning model operating on that robot.
And there's no industry standard for physical AI data provenance yet.
None. The enterprise teams who figure it out first are going to write the rules for everyone else.
This raises an important question, something really profound to think about as we fully transition to this autonomous flywheel.
What's that?
Let's assume you built all of this. You have a constantly updating VLA fleet, continuously learning from synthetic simulations and real-world anomalies, updating its physical brain overnight.
Okay, the ideal scenario.
Right. What happens when that hyper-adaptive robotic fleet has to interact with older legacy software systems on the same factory floor? Or even more complex, what happens when your updated fleet has to share physical space with an entirely different robotic fleet from a competitor?
Oh, wow. Right, a warehouse running Atlas robots alongside legacy automated forklifts or specialized assembly arms trained on entirely different architectures.
Exactly. How will your enterprise data stack handle real-time negotiations between competing AI physical architectures that literally perceive reality, calculate mutual information, and behave fundamentally differently in the same physical space?
That is a staggering thought to end on. Imagine 2 different robots from 2 different manufacturers trying to predict each other's physical movements in real time, relying on entirely different synthetic training environments.
It's going to be chaotic.
It all loops back to that initial splash at CES, doesn't it? The athletic intelligence of that robot doing backflips is incredible to watch. But the invisible data tether anchoring it to reality, the continuous, unbreaking stream of multi-rate telemetry, the math of mutual information scoring, and the simulated physics of synthetic training, that is where the real revolution is happening. Thank you so much for joining us on this deep dive. Stay curious, keep learning, and we'll see you next time.